What if you could visit your past or future today? Imagine stepping into a machine and witnessing historical events firsthand, walking the streets of ancient Rome, watching the construction of the pyramids, or standing beside Einstein as he scribbles the equations of relativity. Or perhaps you'd leap forward, glimpsing humanity's destiny among the stars or confronting the chilling silence of a post-apocalyptic Earth. This tantalizing idea has captivated dreamers, writers, and scientists for centuries.
Time travel isn't just a trope of sci-fi. It's a concept that has permeated human culture, philosophy, and science for millennia. From the ancient Hindu epic Mahabharata, where King Ravana ventures to a higher plane and returns to a future he no longer recognizes, to H. Wells' iconic 1895 novel The Time Machine, humanity has fantasized about bending time to its will. Modern pop culture has amplified this obsession, with franchises like Doctor Who, Back to the Future, and Interstellar exploring the thrill and peril of temporal manipulation. Yet, behind the silver screen spectacles lies a serious scientific dialogue. Physicists like Albert Einstein, Kurt Gödel, and Stephen Hawking have wrestled with time's mysteries, probing whether it's a rigid arrow or a flexible river. Philosophers, meanwhile, debate the ethical and existential implications. Would altering the past unravel reality? Could multiple timelines coexist? As we peel back the layers of theory and speculation, we find that time travel isn't just a narrative device. It's a lens through which we examine the very fabric of the universe. The dream of time travel is fraught with paradoxes and cosmic roadblocks. Take the infamous grandfather paradox. If you journey to the past and prevent your grandparents from meeting, would you vanish from existence? This logical contradiction challenges the coherence of backward time travel. But paradoxes don't end there. The bootstrap paradox, where an object or idea is trapped in an endless loop with no origin, raises questions about causality itself. For instance, what if Shakespeare never wrote Hamlet, and you merely handed him the script during a time travel escapade? Who, then, is the true author? Einstein's theory of relativity revolutionized our understanding of time, revealing it as a dimension interwoven with space. Near massive objects like black holes or at velocities approaching light speed, time dilation occurs, a phenomenon where time slows relative to an outside observer. Astronauts on the International Space Station, for example, age slightly slower than Earthbound humans. But this is one-way time travel, a leap into the future. Reversing time's flow requires bending space-time so severely that it loops back on itself. Theoretical constructs like closed time-like curves, CTCs, paths through space-time that return to their starting point, could enable this, but they demand conditions that defy our current grasp of physics. Wormholes, often depicted as cosmic shortcuts, might serve as time machines if stabilized with exotic matter possessing negative energy density. Yet, such matter remains hypothetical, and even if it exists, the energy required to sustain a traversable wormhole could exceed the total output of a star. Beyond these hurdles, tampering with space-time could trigger catastrophic feedback loops, unraveling the universe's causal structure. Modern physics teases us with glimpses of possibility. Wormholes, first theorized by Einstein and Nathan Rosen in 1935, are solutions to the equations of general relativity. These Einstein-Rosen bridges could connect distant regions of space-time, or even different universes. However, most wormholes predicted by relativity are microscopic, unstable, and snap shut instantly. To make them traversable, physicists like Kip Thorne have proposed lining them with exotic matter to counteract gravitational collapse. Yet, exotic matter isn't just rare. Its existence challenges the classical energy conditions that underpin general relativity. Quantum mechanics adds another layer of intrigue. Experiments with entangled particles, where measuring one instantly affects its partner, regardless of distance, hint at non-local connections that seemingly defy time's flow. Some interpretations, like the transactional theory, suggest quantum waves move both forward and backward in time. In 2020, researchers demonstrated a quantum time loop in a simulation, showing how particles could theoretically interact with their past selves. While this doesn't enable macroscopic time travel, it blurs the line between past and present at the quantum level. Stephen Hawking's chronology protection conjecture posits that the universe might inherently forbid time travel to prevent paradoxes. Laws of physics, he argued, could conspire to destabilize wormholes or CTCs, like a cosmic immune system guarding causality. Meanwhile, Experiments continue to validate relativity's predictions. Atomic clocks aboard GPS satellites, for instance, must account for time dilation caused by their orbital speed and Earth's gravity. These adjustments aren't sci-fi. They're daily proof that time is malleable. So, is time travel possible? The answer lies in a labyrinth of ifs and buts. According to Einstein's equations, forward time travel is undeniable. Accelerate to near-light speed, orbit a black hole, and you'll outpace Earth's timeline. But reversing time's arrow? That's a different beast. Prominent physicists are divided. Kip Thorne, who consulted on Interstellar, asserts that CTCs are mathematically consistent but likely unstable. David Deutsch, a pioneer in quantum computing, argues that paradoxes could be resolved through the multiverse, a branching network of timelines where every choice spawns a new reality. In this view, killing your grandfather wouldn't erase you. It would merely strand you in a parallel universe. Others, like Hawking, remain skeptical, citing the absence of tourists from the future as evidence against its feasibility. Technologically, the barriers are astronomical. Stabilizing a wormhole would require energy densities akin to collapsing stars, and harnessing such power is beyond our civilization's reach, perhaps forever. Even if achieved, the ethical implications are staggering. Who controls time travel? Could it weaponize history? The universe's laws, as we understand them, seem to erect a fortress around causality. Yet, science thrives on rewriting the impossible. In the grand tapestry of cosmic mysteries, time travel remains one of the most electrifying and elusive threads. Relativity and quantum mechanics have nudged open the door to theoretical possibilities, but paradoxes, energy constraints, and existential risks loom large. For now, our temporal voyages are confined to imagination, the pages of novels, the frames of films, and the chalkboards of physicists daring to ask, what if? Yet, the pursuit is far from futile. Each equation, each experiment, peels back another layer of time's enigma. Projects like the Large Hadron Collider and quantum computing research inadvertently probe the foundations of spacetime. Perhaps one day, a breakthrough, a unification of quantum mechanics and gravity, or the discovery of exotic matter, will transform fiction into fact. Until then, time travel remains a mirror held up to humanity's curiosity, ambition, and humility in the face of the cosmos' grandeur. What's your theory about time travel? Could wormholes unlock the past, or are we forever chained to the present? Share your wildest ideas, favorite paradoxes, or even your own sci-fi screenplay pitch in the comments below. If you're craving more cosmic adventures, smash that subscribe button and dive into our playlist on black holes, portals to the unknown. For the ultimate deep dive, don't miss our 45-minute special, Einstein vs. Quantum Physics, the War for Reality. And as always, stay curious, fellow time travelers. The future and past await.